Okay, so if we look at this first number, the cube root of 16, are there any perfect cubes that are factors of 16? 16 is 8 times 2. 8 is a perfect cube. So what does the cube root of 8 simplify to? A base of 2. So that comes out as a 2. And notice this factor of 2 is going to stay inside our radical. Okay, so now we go to the next base, x's. Okay, so we're looking we're looking for groups of the index, so groups of 3 that we can remove from 3. So how many groups of 3 can we remove from 3? 1. So that comes out as x to the first. And when we remove one group of 3, how many x's are going to stay inside the radical? None. We took out all 3 of them. So there's no x's left inside. Now let's look at the y's. How many groups of 3 can we remove from 5? 1, so that comes out as a y. And that when you remove one group of 3, how many y's are going to be left inside there? 2. Okay, and so now when we look at this, do we need to consider absolute values? Remember, what's the rule for when you need to identify or look for absolute values? The index has to be an even number. Since this index is an odd number, do we even need to worry about absolute values? No. So just leave it. That's as far as you have to go. Right.
Okay, how to do the x and y?
So when we look at this, remember this is really like cube root of 8 times the cube root of 2. So if you factor the number that's inside, and you can remove a perfect power. So here, the cube root of 8 is a 2, so that's going to come out. It's 2 cubed, right? Okay. So you always want to look at, in terms of the factors, are there any perfect powers you can remove? So with the square root, so this next one, now be careful, can you guys see the difference between this 3 as being multiplied rather than the index? Okay. If you ever have a question on that, and you're taking a quiz or a test, or even homework, ask me. Okay. But you should be able to see the index is the same size font as the powers. It's just going to be located right above that, like kind of right inside that radical. Any numbers that fall outside of it are just multipliers or coefficients. Okay, so here when we look at this square root, let's start with the numerical base. Are there any perfect squares that are factors of 200? Yeah, this is 100 times 2. So the square root of 100 comes out as a 10. And the factor of 2 stays inside our radical. Again, notice as I write these, I keep my 3 out front, and then I include my simplified form of square root of 100, and I leave a space to account for the other variables. I create my radical, and I just kind of keep a running total. The factor of 2 is going to stay inside here. And so now we're looking for groups of 2, whatever our index is. So how many groups of 2 can we remove from the x's? We have one group of 2, so that comes out. When we remove one group of 2, how many x's will stay inside our radical? None. We took out the one group of 2. There's nothing left inside. Okay, how many groups of 2 can we remove from the y's? 1. And that leaves how many y's inside our radical? 1. And then how many groups of 2 can we remove from our z's? None. So the z stays inside. Okay, so here is our answer. 30 xy square root of 2y z. Right now, before we can finish this, we have to check for absolute values, right? Because our index originally was an even number. So let's go in and see. Okay, can x be a negative number in our original form? Yeah, we're going to square it, then we can take the square root of that. So it's not tied to any other numbers or any other variables. X may or may not be a negative. So we have to make sure that that alone is accounted for. So what do we need around our x here? Absolute value around the x. Okay, let's take a look at our y's. Okay, can y be a negative number? Yeah, but if y is negative, what other condition has to be true? If y is negative, the only way for this product inside the radical to not be negative is for what other value to be negative? Z. So y and z are either both positive or both negative. So again, we have to consider the fact that y and z may be negatives. Is that possible? Well, in our simplified form, when we look here, The y times z inside the radical is going to be fine. But what about the y on the outside? No. So we have to include absolute values around that as well. So I'm just going to let me ungroup this real quick. Oh, I'll have to erase it. Okay, so the absolute value doesn't just go here. The absolute value has to go around the y as well. And so we get our solution to look like this. The product xy has to have absolute values around it. Okay, finally, our last example here. Okay, so here we can simplify this. Again, the power and the index can have no common factor, so we can cancel those. So 3 goes into 6 how many times? 2. So really we're looking at the square root of t. And now, because our original index was an even number, 6, we do have to test for absolute values. So could t have been a negative in our original form? T cubed gives us a negative, then take the 6th root of that. So can t even be a negative? No, it can't even be a negative. Well, is that restriction demonstrated in our simplified form as well? Yeah, because t still can't be a negative here. So we don't need anything around it. There's not even a case where t is going to be a negative value anyway. So that's all you need to do for that. All right, I have 3 more problems that I want you to try. They're not in the book, so I'm going to write them up here. Just take a moment or two and see if you can answer these, please. All right, so let's talk through these here really quickly. So we're dealing with the cube roots here, so we're looking for powers or groups of 3. So how many groups of 3 can we remove from the x's? 2, so that comes out as x squared, and how many x's would be left inside our radical? 2 groups of 3 is 6, leaving 1 inside. Okay, now we can move to our next base. How many groups of 3 can we remove from the y's? 3 of them, which leaves how many inside the radical? None. And so do we need to consider absolute values for this? No, the original index was odd, so you don't even need to worry about that. You've simplified it and you're done. So this would be our simplified form. Okay, what about example E? It's pretty similar to C. The difference is we have an index of 6 and a power of 2, so we can still reduce it. What common factor goes into both of those? 2 goes into 2 goes into 2 once, 2 goes into 6 3 times. So we're looking at the cube root of t as our simplified form. And so now we test it for negative since we had an original index that is a 6. And so could t have been a negative in our original form? We're going to square it and then take the 6th root of it. Yeah, that still works. So we can simplify it. T can be a negative. Okay, now, when we look at the original form, we know because the original index was a 6 that this whole thing has to be greater than or equal to 0. Is that restriction demonstrated in our simplified form? It's not, right? Because t could be a negative, and if you took the cube root of it, you'd get a negative value. But we know, based on the original form, that that can never be negative. So what do we need to do with the t? We need to include absolute values. Okay, so again, when you look for your simplified form, you have to refer back to the original form as well, not just what the simplified form looks like.